Hello, friend. My name is Derek Harder, and in this video, we're starting on a section where we're going to do an introduction to applying deep learning to computer vision. So in this video, we're going to look at what are known as convolutional networks. So these are really kind of our first example of what we would consider deep neural networks. So we've mostly been using what would have been thought of as just neural networks before. So convolutional networks and convolutional layers are especially good for doing image processing, so things like image classification or image segmentation or things like that. So in this video, we'll try to give you a little bit of a introduction to how convolutional layers and max pooling layers work. But let's first start with just a quick example of what a convolutional network is. Okay, so let's go ahead and get started. So before I try to get into the details of what convolutions are and max pooling and how they work, let's revisit the MNIST digits task that we looked at before. So we used this previously. One of the examples we saw was just a sequential connection of densely connected layers. So it would have been considered like a regular neural network, maybe a little bit deeper than people would have seen before, had like 2 or 3 layers. And we got like 97-98% accuracy on that example when we showed it the first time. So in the following here, this is an example of a small convolutional network. Sometimes some people call these convnets. And if you look at this, this is using the Keras functional API that we've introduced you to before. It's just a sequence of convolutional conv2D layers followed by max pooling layers for the most part. Okay, so we'll go into the details of this. I just want to point out a couple of things of this. So these are just layers that we haven't seen before that you can use in Keras. So notice, if you're paying attention, if you remember what we did before, there's no flattened layer between the inputs and our convolutional layer, right? So recall the MNIST data are 28 by 28 pixel images with one channel. So they're just grayscale images. So there's no color. So we call that, it's 28 by 28 is the size, and there's one color channel coming in. And that comes directly into the convolutional layer. So a couple of things to point out when you're looking at this. Let's go ahead and run it so we can define our model here. So notice that we've got these convolutional 2D layers. Notice this filter parameter increases as we go among layers here. So it starts at 32 filters, then 64, then 128. Okay. So this is a common pattern here. We'll talk about that. Notice that the kernel size we're using is 3 on these. So we'll learn what a kernel is for a convolutional layer here. And also, I'll point out the parameter for the max pooling layer. So this has a pool size of 2 here. And we'll talk about what these max pool layers do. All right. Notice, the convolutional layers are similar to the dense layers in that they do a tensor operation, a kind of tensor operation, and we normally have an activation function. So we just use the standard RALU activation as output. Notice the max pooling layer doesn't do an activation. It's kind of different. It's not really doing the same as like the dense layers you're familiar with, right? And since this is MNIST, the output, we'll have to talk about this, doesn't come out flattened. So the flattened layer that we kind of had before actually comes at the end now instead of the beginning. So after this last convolutional layer, we flatten, and then we see the normal stuff you should be used to here. So we have a dense layer. Since this is a 10-class multi-class classification problem, we just use softmax with 10 outputs for our 10 classes. Okay, so let's look at the summary here. Just a few more things about this. So these details will make more sense, but pay attention here to, for example, the output shapes coming through here. So notice for our input, it comes out as 28 by 28 with one channel. So the 32 filters for our first convolutional layer ends up being the output for the first convolutional 2D layer and out of the max pooling layer. Right, so there's 32 channels. So the image size changed a little bit, 26 by 26. Also notice that the main function of a max pooling layer is to downsample. We'll go into more about that in a bit. So notice the size has been reduced by half. So it went from 26 by 26 to 13 by 13. So a similar thing happens for the next 2 convolution layers. So the next convolution layer had 64 filters, so now there's 64 channels here. and the next match pooling layer actually pretty much have these. And then the last convolution layer had 128. Okay? So that's a common pattern. As we go through a convolutional network, the number of filters will increase as we go down the hierarchy, but the size of the image, you should think of these as feature maps. So it's an image when we start, but these are feature maps as we go down here. So the size of these will be reduced steadily as we go down through the hierarchy, right? So at the end, when we flatten these, you end up with 1,152 inputs into the final dense layer that makes the final decision about which of the 10 classes it is. Okay, so let's just see the performance on this real quickly here. So we'll load our data, we'll compile the model with the sparse categorical cross entropy, which is good for doing a multi-class classification problem, and we'll run it for 5 epochs here, so it shouldn't take too long to get through these. Let me pause. So if you looked at this, I mean, the training loss did really well. The training accuracy did really well, above 99%. But that doesn't really tell us how well it can generalize. So let's evaluate it on our test data that it never saw before. So we got 98.83% here. So that's actually a little bit lower than, on average, you'll get over 99% on the final test accuracy. So around 99%, 99.1%, which is significantly better than the 97 or 98% that we got with the just sequence of dense layers, okay? So why does a simple convolutional network like this do so well compared to a densely connected layer? So to answer that, we have to look at these convolution layers and the max pooling layers and what they're doing. Let's do that. So the fundamental difference between a densely connected layer that you're familiar with and a convolution layer is that the dense layers learn global patterns over all of the in their flattened vector space, right? So remember, dense layers basically just take a vector of features that come in, so they can only learn a pattern kind of global on that. So for a convolutional layer, we're going to pass it in still as a two-dimensional shape like this. So convolutional layers learn local patterns. In the case of images, patterns found in small, usually 3x3 grids. All right, and so that's what the features of the output channels, the output features of a convolutional 2D layer are. Is that they're going to be looking over this this image, and they're going to try to learn patterns like I'm going to try and detect a diagonal line like that, or a horizontal line, or maybe I build a pattern or a filter that detects a shape like a curve like that or that, right? So then the windows are slid over here, so for our first layer we had 32 filters, so there would be 32 filters like this. That it learns. So it tries to, so the types of filters that are typically built are things like edges, horizontal, vertical, certain kinds of curves and things like that. So then the output from the convolution is going to be, for the 32 filters I learn, was there a diagonal line here, or was there a curve, or so on. All right. So that's kind of the basics, what a convolutional 2D layer does. So technically, this is known as being translation invariant. So the patterns that a convnet learns are translation invariant. So it might see a diagonal here, but and respond to it. But if there's a diagonal here, it could respond to it there. It's doesn't matter the location. It'll look at all these 3x3 patches over the image and see if any of the filters it learns to recognize are on that place or not, and respond to that. Okay, so that's kind of what we mean by translation invariant. So again, to restate that, after learning the pattern in the lower right corner, a convolutional network can recognize it anywhere on the two-dimensional space of the image that it's scanning over. Okay, and this makes convolutional nets very efficient because the visual world is fundamentally translation invariant. Okay, so that's just a statement we make, but it is generally true if you think about it. So the second key property, so the first one was learning these translational invariant patterns or filters. So the second key property of convolutional networks is that we can train them to learn spatial hierarchy. So this makes them very powerful and kind of similar to the way that visual systems in mammals and humans work, at least the way that we think they work. So convolutional networks are capable of learning spatial hierarchies. So if you remember back to our previous example, we had basically 3 layers of a hierarchy. So in this diagram, we go from low level. So like our first layer in the previous example had 32 output filters, and then 64, and then 128. So in this figure that's trying to represent what kind of typically happens on this convolutional network, the first layer tends to learn simple, small patterns. So it tends to be like edge detectors, things like that. For example, on the second layer, if we're building a image classifier to learn if it's a cat or a dog, so the second layer might take these as input and start to learn higher level features in the hierarchy, like this pattern is an eye, or this pattern is a nose on the picture, or this one kind of looks like an ear, right? As a combination of several of the features that are output from the convolutional net on the previous layer, right? And if you keep going up, building hierarchies like this, so maybe the next level identifies, this is a face, or something like that, right? So this allows convolutional networks to efficiently learn increasingly complex and abstract visual concepts. This is useful because it tends to be that the visual world, the real world, is fundamentally spatially hierarchical in the same way, all right? So the operations that happen in the one of those convolutional 2D layers can be described as this. So convolutions operate over a rank 3 tensor. Okay, so remember that for the first convolutional layer, the input came in as a 28 by 28 by 3 image. So there was 28 by 28 pixels, so 2 spatial axes, and 3 color channels that came in. So what happens is that a convolution operation extracts patches based on the kernel size. So our kernel size was 3 by 3. So it means that it looks at 3 by 3 windows on this input image, and it applies the same transformation on all those patches. So it's applying a tensor transformation on each one of those patches to produce its output. So again, the output of a rank 3 of a convolutional operation is again a rank 3 tensor. It has a height and a width, which you'll see for our first convolutional network was 26 by 26. So it went from 28 by 28 to 26 by 26. And it has a depth. I don't know maybe I shouldn't have said arbitrary, but that depends on the number of features you ask it to learn. So since we asked it to learn 32 features, what that first convolutional layer tries to do is learn 32 separate 3 by 3 kernels. And it will eventually learn kernels like a horizontal line or a vertical line or features like that usually for the first layer or the most useful kind of features. Okay, so those filters, these 32 filters on that first layer that make up the output of this rank 3D tensor encode specific outputs of the input data, and they detected on each of these 3 by 3 patches. Okay, so basically the convolution scans over the image. And so for the first filter that's like a horizontal line, it looks at every possible 3 by 3 patch and it detects, okay, is that kernel, is that horizontal line, do I detect it in this 3 by 3 patch or not, for every 3 by 3 patch that comes as input. Okay, so at a high level, a single feature, so at a low level, they tend to be things like edge detectors. At a high level, a single filter could encode concepts like presence of a face, presence of a paw, presence of a tail, presence of a tusk, things like that. Okay. So just to summarize that on the MNIST data, I just skipped ahead a little bit here on the previous one, so I was a little bit wrong. So normally we're going to be working with color images, so it'll come in as RGB with 3 channels. But yeah, the MNIST data is actually just a 1-channel input because it's grayscale. So that for the first layout, it comes in as like that. So we'll see why it gets down to 26 by 26. But since it was creating 32 features, 32 filters was the name of the parameter was filters for the convolution 2D. It outputs a 26 by 26 by 32. Okay, so it's basically learning 32 filters over the input, right? So this is an example of a single filter, like a kind of a horizontal line in that direction there. So each of these 32 output channels contains a 26 by 26 grid of values, which is a response map. So this is the response. So if this is the one of the 32 filters here, let's say this is filter number 1 of 32. This might be the response map for the input over here that, it responds most highly, that it sees a diagonal line like that there and like there and there, right? So that's kind of what these outputs are. So for there's 26 by 26 outputs, and there's 32 channels. Each one of the channels would be something like that. So another filter might have been like a horizontal line. So you get a response map for a horizontal line and so on. So to summarize that a little bit, the feature map is that every dimension in the depth axis is a feature map, okay? So there's the length and the width, and then however many features or filters that you specify represents a feature map in the third dimension, or the depth axis, okay? So the rank 2 tensor output from a convolution of 2D is a 2D spatial map of the length and width of the response of the nth filter over the input. Okay, so, and we've already stated this, the convolutions, there's 2 key parameters, the size of the patches, that was called the kernel, and then the depth, or the number of output feature maps. So that's the number of filters or features, and that parameter is called filters for the convolution of 2D now. So the tensor transformation that happens inside of a convolutional layer works like this. So if this is the input, and if we're using a 3x3 kernel, basically the width and the height, we would scan every possible 3x3 kernel, right? So here we're showing one 3x3 kernel, and like our MNIST data had a depth of only 1. Kernels are one of the windows that we'd look at. So for the MNIST data, the depth of the input would just be 1. If this was color data, we would have 3 channels coming as input, okay? So for each one of these patches like this, we apply our tensor product here. So the dot product with our kernel, right? So the kernel, like if we ask it to do 32 filters, the result of that dot product times this 3x3 by 1 or 3x3 by 3, if we had 3 color channels, would be a single vector with 1 output for each one of the filters, right? So if we have 32 filters, the output from that dot product would be 32 values, which would be the response for each of the 32 filters we're trying to learn of whether we see it in that 3x3 patch or not, okay? And then that happens for every 3x3 window. So for example, if this 3x3 window here, if we pull it out, and again, if it was grayscale, there would only be 1 color channel. If it was a color image, it would be a 3x3 by 3. We would have 3 color channels. We do the dot product of the same kernel, we would end up with 32 outputs, and that gets reassembled. So that's why the output from the convolutional 2D layer is also a 3D tensor, right? So we have a width and a height of like our 2-dimensional image, and then the depth is the number of color channels or the number of features that we are learning for this convolutional layer, okay? So, like you noticed, like for the first layer, the pixels, the images come in as 28 by 28, but they came out as 26 by 26. But that's easy to understand because of these border effects, right? So here we've got a 5 by 5 image. So if we're using 3x3 kernels, so here's our first one, right? So you can only actually get 3 3x3 windows that don't go over a border. That's the first one. That's the second one. And then this is the third one here, right? Same for the middle, and then same for the bottom, right? So on a 5 by 5, if I'm scanning with a 3x3 kernel, I end up with a result of I have a 3 by 3 by whatever the number of filters are as my output, okay? So basically, if you're scanning without filling in the borders here, you'll have two less, right? So for a 28 by 28 size image, I only am able to get 26 by 26 valid full-size 3 by 3 patches, when I scan over the input. So we'll see some situations where you don't want to have it reduced by 2 pixels on the width and the depth by doing that convolution. So, you can just add padding. So padding consists of adding appropriate number of rows and columns. Usually, I think the default is to just copy the pixel value for the row next to it. Or it might be just add zeros. I'm not certain what the default is, but you can just add, a row before and after and a column before and after. Then with that padding, if I'm doing if I have 28 by 28, if I use padding, I'll get 28 by 28 on the output. But also be aware that we can do strided convolution. So instead of moving my 3 by 3 patch 1 pixel each time, I could move it 2 pixels or 3 pixels. So the result of using a stride is that you would actually be downsampling, right? So if I stride by 2, originally, and let's say we were using padding, right? So, but if I strided by 2, originally by 28 by 28 would only come out to 14 by 14 valid 3 by 3 patches if I move by 2 pixels, to the right and 2 pixels down each time. Okay. But, so that's a way to do downsampling, and that's used in some cases, but usually downsampling, we're going to use the max point operation. So let's look at the max point operation, what it does to downsample these feature maps. Actually, before I do that, just real quickly, so I was describing this, but for example, adding padding. So our previous 5 by 5 example, what we mean by padding is we just add, 2 columns and 2 rows. So again, I think these usually default to like copying the pixel values or maybe just taking the average or maybe 0. I'm not certain what they do for the pads there. But yeah, if we're doing a stride size of 1, then we can end up with the same output size as input size. So there's actually a 5 by 5 valid 3 by 3 kernels if we pad by 1 row and 1 column on each edge. Okay. So we don't end up reducing the size by 2 by doing that. And then striding, so again for a 3 by 3, our first 3 by 3 would be here. That gives us this one. So if we stride by 2, we would just go over. So our next 3 by 3 would be this one right there, right? So, and you can stride by 3 or 4. So if you stride by 3, you'd be downsampling 3 times. Stride by 4, it would be 4 times smaller and so on. So the max pooling, though, is usually the preferred, except for particular situations, to do this kind of downsampling. So remember, we talked about when you go through the hierarchy of a convolutional network, the number of filters increases, but the size of your feature maps, the width and the height, usually needs to decrease. We'll talk more about why that is in a bit, but the preferred way to do that decrease, to do the downsampling, is to use what are known as max pooling layers. Okay. So the role of the max pooling layer is to aggressively downsample feature maps. So one reason why we need to downsample is we don't want our networks to get too big, so it's an overfitting argument, right? So if we don't downsample, you're going to have millions of items that come in to your final dense layer. Okay. So basically, this works in a similar way. We slide windows. So typically, if we want to downsample by 2, we would slide 2 by 2 windows. But we're not doing any tensor transformation here. So there's no learning that happens on max pooling. It's a simple transformation where if we use a 2 by 2 window, whatever the max value is of those 4 outputs, those 4 features in that window, it would just output the maximum of those. Okay, so that's what max pooling is. So you can do average pooling and things like that, but we usually just do max pooling. So you'll see that most of the examples we use in this textbook are going to use a convolution with a kernel size of 3 by 3 and no stride, and then use a max pooling to downsample by 2 using a 2 by 2 max pooling layer. So real quickly, again, to answer that question, so why do this kind of downsampling? So let's look at the first example, but let's remove the max pooling layers and see the result on the number of trainable parameters on our network. So here we're just doing the convolutional layers, the same ones as before, but we remove the max pooling. So if you look at that network, you'll see that there's 61,952. So the size reduces by 2 by 2 each time, but it's still 22 by 22 by 128 when we flatten to go into the last layer. So there's over 50,000 parameters, whereas before there was only 1,000, a little over 1,000 we had before. Okay, so what's wrong with that setup? So it's not conducive to learning spatial hierarchy. So what happens here is that these are still, we want these to be big features, okay? So down here, these are still really, if you go back and see where these map to spatially on the original input, these are still relatively small spaces of the input. All right? So what we really want on this last layer is things that are over the whole, so recognize a face is on this whole layer, or where it is in the first the upper left quadrant, upper right quadrant, something like that, right? And also I already made this argument. So you end up with a large number coming in here that can lead to overfitting. Okay. All right, so just quickly to summarize this video, we went over the important aspects of convolutions and max pooling layers. So keep in mind that the world is fundamentally translation invariant. So when we're doing computer vision, like image classification tasks or doing something with images, convolution layers can learn translation invariant kernels. So they can be very efficient computationally and perform much better than a dense layer that has to learn a similar kind of pattern, but without the hints about, things are spatially local to each other, translation invariant. Also, the world is fundamentally spatially hierarchical. So, and that tends to be what happens if you set the layers the way that we showed, where they go through successive layers that learn more and more features on smaller and smaller, smaller and smaller. The size gets smaller for the width and the height, but really what that represents, if you translate it back, is larger and larger areas of the original area. Okay, but that basically allows convolutional networks that have a sequence of these to learn a spatial hierarchy. Okay, so convolution layers operate by sliding windows to extract patches, and they apply a tensor operation called a convolution. They apply a tensor operation called a kernel on each one of the patches to get the output. So every one of those, the depth dimension, that third dimension, is a feature map. So it's the response of some kind of a learned feature, like a horizontal edge or a vertical edge or things like that. And the role of max pooling is to aggressively downsample feature maps. So they don't actually have any learning parameters. They just always take their inputs and combine like a 2 by 2 or 4 pixels into a single output. So that's it for this video. I hope that that stuff was useful for you for understanding basically how convolutional networks work. And I hope to see you in our next video.